Hi everyone, here and at home. We're starting with the second example because I learned from the last class that this example is easier than the first one. So if you're doing this from home, find the second example, and that's where we're starting. So it says a Norman window is a rectangle with a semicircle on top. Determine the dimensions of a Norman window that would let in the maximum amount of light. The perimeter has to be 10 meters. Okay. So first thing we want to do is figure out what it is we're maximizing or minimizing. And we want to let in the maximum amount of light for this window, which means actually, what are we maximizing? The area. So the area is going to be the area of the semicircle, which I'll just draw a little picture, plus the area of the rectangular part. Everybody good with that? And you have that formula sheet to use if you need to. So what is our formula sheet, or how could it help us get the area of a semicircle? Anyone? Owen.
The circle 1 divided by 2.
Circle divided by 2. So the area of the circle is pi r squared. So the area of a semicircle is going to be a half pi r squared, or you can just say pi r squared over 2. Everybody good with that being the area of the semicircle? I'm just going to draw on here then that this represents the radius. Okay? So if that represents the radius, and I'm trying to figure out the area of the rectangle, how long is this bottom side?
2.5. Oh, 2R.
2R. Okay, good. 2R. Everyone see that? With respect to R, it's 2R. And then this side is something else. I could call it X. So the area of the rectangular part is 2R times X, or 2RX.
Doesn't matter if it's called X or Y, as long as it's equal to variables.
Right, it doesn't matter. Okay, so just a sec, I'm going to pause this. No, actually, you explain to yourself at home why this 2RX is the area of the rectangular part. And then I'll just pause. Red. Oh, you're right. Okay, welcome back. Okay, now we have to get this in terms of one variable only. And I see that my first term only contains R, so I want to get everything in terms of R. So I'm going to have to figure out how to rewrite X in terms of R. And there's a piece of information in the question that we haven't used yet. Does anyone have this?
10 meters.
The 10 meters, okay? 10 meters is the framing. Everyone see that? So that 10 meters has to be the 2R's here, the bottom of the window, this side of the window, this side of the window, and then this wavier semicircle side of the window. Now, if I looked at my formula sheet and I found the circumference of an entire circle, it would tell me that the circumference was 2 pi r. Everyone see that? But I only want half a circle, so I have to divide that by 2, which is just going to give me the pi r. Okay? So I want to get the x's together. So I've got 10 equals 2r plus 2x, because these are like, plus pi r. And I want to get x by itself, so I'm going to subtract 2r on both sides and subtract pi r on both sides. So these are gone, these are gone. So I end up getting that 2x is going to be 10 minus 2r minus pi r. But I don't want 2x, I want x, so what am I going to do? Divide everything by 2. So I end up getting x is equal to 5 minus r minus pi over 2r. Yeah? So I come back up here, and I'm going to replace that x with 5 minus r minus pi over 2r. And now I have that all in terms of r. Now I want to make the prettiest, easiest version of it to derive. Okay? So I'm going to distribute this.
Clarify, is the pi and the r in the numerator over 2?
Yep. Yep.
But you can just split the r as kind of to the side.
I thought it had it up there. No. So that's going to be plus 10r minus 2r squared. And then what happens when I multiply 2r by minus pi over 2r? Minus pi r. R times r. Minus pi r squared. Yeah? Okay. And that's where r is the radius, so it has to be greater than 0. Okay? So if we got a negative critical value, we would ignore it. Does it make sense for the radius to be negative? Yeah? Okay. So now we're going to find a prime at r. Because now we've made it easy to derive. So we can just use the power rule. And that's going to give us pi r plus 10 minus 4r minus 2 pi r. Yep.
Doesn't the square of the 2 belong to r to the radius?
Sorry?
Like if you derive 1/2 pr squared, does the 2 belong just to the r?
So I multiply the 2 by the 1/2.
Yes.
And then reduce the exponent on r by 1.
Yeah, but like on pi, it's r, 2 is just r squared. Pi is not squared.
Pi is not squared. It's pi times radius squared. Okay? Yeah? Okay, so now we want to set this equal to 0 and solve for r. So what we want to do is get all our terms with r on one side and our terms that don't have r on the other. Okay, so we can common factor that r out. Okay, then? So I'm going to, I think I'll keep the 10 positive, so I'm going to add 2 pi r, over here. So that's done. Add pi r onto this side, or subtract pi r, my bad, sorry. Subtract pi r, so it's over here, and add 4r. And then the only thing left on this side will be the positive 10. And I just noticed, what's 2 pi r subtract 1 pi r? Pi r. And now to get r by itself, I want to common factor the r out of this side, which means I'm dividing each of these terms by r. So I would get pi plus 4, which means now I would divide both sides by pi plus 4. Remember, pi plus 4 is just a number. So we've got our critical number is 10 over pi plus 4, or approximately, make sure you use brackets when you're putting the pi plus 4 into the denominator. So 10 divided by pi plus 4. I got 1.400. Yeah? And what were we measuring in? Meters? Meters? All right, I'm just gonna pause it for a second. All right, so we found our critical value. We want to make sure it corresponds to a maximum. So we have to find the second derivative. So where's an easy way? Here's our first derivative. So I'm going to come from here and find a prime prime at R. Okay, find my second derivative. And it's going to be pi minus 4 minus 2 pi. These are all just numbers, and these numbers I can combine. So a prime prime at R is pi minus 2 pi is negative pi minus 4. And this is a constant. It's like roughly negative 7.14, right? Roughly. So it's a constant, which means a prime prime at 10 over pi plus 4 is also negative pi minus 4, which is less than 0, which means we've got our maximum. So R being approximately 1.4 corresponds to our maximum area. Okay? And the question wants to know the dimensions of the window. So I guess we'd say if we were giving dimensions for the window, we'd say the radius is 1.4. How are we going to get this x? How are we going to get how long x is? Owen. Yes. So this is the easiest form of that 10 equals thing that Owen was saying up here. So I've got x equals 5 minus 1.4 minus pi over 2 times 1.4. Does that make sense to everybody? So I'm going to find x out now. So x is going to be 5 minus, so I'll put approximate here, 1.4 minus pi over 2 times 1.4 is approximately I got 1.4 again. So if I look at my picture, I'll write a sentence out in a second, but this is 2R, so this is going to be about 2.8 meters. Does that make sense to everybody? Diameter. And then this distance here is going to be about 1.4 meters. Okay, so that's how the window should be built to maximize the area of sunlight. So we just summarize that in a sentence, yeah?
Do we have time like the dimensions of the semicircle as well, or no?
We have, if by saying the diameter is 2.8, you're giving them. That's all you need for a circle, right? So it's the radius to get the area. Scroll down. Yeah. I'm going to write my sentence anyways. Yeah, so scroll down here. Okay, so therefore, the diameter of the window should be 2.8 meters, and I'll call it rectangular side length. I don't know really what to call it. X in our picture should be 1.4 meters. Okay, so I'm going to pause there while everyone Okay, welcome back to classic optimization questions. We're now trying the third question in the lesson. And it says a can must be manufactured so it can hold 1.5 liters. Oh, it should be an S there. 1.5 liters of oil. Find the radius of the can that will minimize the cost of the metal. And it also gives you that 1 liter is the same as 1,000 centimeters cubed. Okay, so I'm going to start off by drawing a diagram of the can. Okay. And a can has a radius and a height. And if we are minimizing the cost of the metal, what is it about the can that we're actually minimizing?
The material.
The amount of metal you need, which is the area. Okay? Now on your formula sheet, can you find an equation that tells you the area of a cylinder?
Yeah.
And what is it, Owen?
2A times base plus.
Of a cylinder?
Oh, here it is. 2 pi r squared plus 2 pi r.
Yeah.
I'll just read this.
Okay, so there's the area of a can, and in this case, the can has like the top and bottom. That's the 2 pi r squared part. Okay, a variation on this question would be an open top can. Okay, but we're doing a closed top can for this question. So that is our formula. But now we have to get it so it's all in terms of R. So there has to be a way in the question to get H in terms of R. So what piece of info have we not used yet?
The volume.
Yeah, the volume. Love that. So we know the volume is 1.5 liters or 1,500 cubic centimeters. And the reason we're converting it to centimeters is because we know our radius and height are going to be in centimeters, not in meters. Does that make sense to everybody? Yeah. Okay. So we've got, is there a formula for volume of a cylinder on your sheet? And it is?
Pi r squared times h.
Pi r squared times h. And we know the volume is 1,500 cubic centimeters. And how would I get h by itself? Divide by pi r squared. Awesome. So I've got that h is equal to 1,500 over pi r squared. And now when I come over here, I can make a as a function of r. So a at r is 2 pi r squared plus 2 pi r times 1,500 over pi r squared. Remember, we want to make it as easy as possible to derive. Does anyone see any interesting stuff that's going on here?
We come to 2 pi r.
We could, but that we're not going to because we don't want to use the product rule. Vanessa?
First, pi r squared to the -1.
Okay, so you're jumping steps here. So the pi and the pi, agree? Yeah? How about if I have an r here and an r squared in the denominator?
Get rid of all the parts.
There's going to be 1 r down here, and that's why Vanessa's saying bring it up. And then what about my 2 and my 1,500? Multiply them together and get 3,000 r to the -1. So I'm going to pause it here. So people at home, make sure you understand how to get from this step here to this step here. And then we're also going to do that in our class. So here we go. All right. Okay. And can we agree that the radius has to be greater than 0? So if we get a negative radius, we would ignore that answer. Okay, disregard it. All right, so now we want to find a prime at r. We're going to find our critical number or numbers by finding a prime at r and setting equal to 0. solving for R, any R values we find will be our critical numbers. So that's going to give us 4 pi R minus 3,000 R to the negative 2. Yep. Okay. Now we're going to set A prime at R equal to 0. And write it like that. Okay? And we've solved equations like this for the last few days. So what I want to do is add this fraction part, add the 3,000 over R squared to the other side. And then how do I get the R so it's all in one spot? Oh, and yeah, multiply both sides by R squared. Very good. So on this side, those R squareds divide out. And I get 3,000 equals 4 pi, and then R times R squared is R cubed. Yeah? First, before third root, what do I do? Divide by 4 pi. Yes. Okay, divide by 4 pi on both sides. So R is going to be the third root of 3,000 divided by 4 pi. And then make sure you can get an approximation for that on your calculator. Use brackets around the 4 pi when you're entering it in for most calculators, or you won't get the correct number. And you guys get 6.2 approximately? Okay. 6.2 centimeters. And now we want to make sure that corresponds to we want to minimize, right? Corresponds to a minimum. So that means we have to find a prime at R. Okay. And make sure that when we sub in 6.2, we get a minimum or a positive number. Okay. So then that's where we use our second derivative. It's just to make sure whether we have a max or a min. So A prime at R. In the mode, find our second derivative here. So that's going to be 4 pi plus 6,000 R to the negative 3. So A double prime at 6.2 is approximately 4 pi plus 6,000 over 6.2 cubed, and all we care about is that that's a positive number, which means that we have a minimum. So we've minimized the amount of metal we need if the radius is 6.2 centimeters. Okay, then we go up, make sure we see what the question's actually asking us about. Find the radius of the can. That will minimize the cost. So we've got that, we just need our therefore then. So therefore, the radius should be 6.2 centimeters to minimize the cost of the metal. Yeah.
It seems like for those problems, when we're solving for the max or the min, we always get the result we're expecting. Is there ever going to be a problem where it's like we're looking for a max, but for some reason we're getting the number we found as the minimum?
Only if there's more than one critical number, right?
Oh,
Then one may correspond to a maximum, or one may It's just good practice to do this. So that, yeah. So that you It'll also show you if you made a calculation error somewhere, like if you accidentally got 13 here or something went wrong, and you're double checking yourself.
Also, did we lose marks for how we word our Air Force statements?
No, as long as you answer the question, I don't have to use the same words as me. Just make sure you answer the question asked. Like if it says, what is the minimum area, then you have to plug 6.2 into the area. Okay? All right, so now we're going to the first one, which turns out was the most challenging, but it's my favorite. Love these ones. Another classic. Very good classic. It's the cable laying problem. All right. So, in this case, we have an island 4 miles upriver from the power station. So that's telling me that from here to here is 4 miles. Okay. And 1 mile out from shore. And it's going to be connected. We're hooking up the island with cable. It costs $30,000 per mile to lay cable under the ground and $50,000 per mile to lay cable under the water. What is the least expensive way to lay the cable? So this is telling us that we want to minimize cost. Yeah? Minimizing cost. And can you guys agree with me that the cost is going to be made up of the cost of underground plus the cost of underwater. Yes. Okay. So this is how we do things. They're very fun. Hopefully you like them as much as me. So I'm going to put a little right angle there. And actually use the word hypotenuse, which I love. And I'm going to have this distance here in blue be x. Okay? If this distance here is x, what is the distance from here to here, from the power station to where I'm going to veer off underwater? 4 minus x? Yes? 4 minus x? And now I'm deciding, okay, I'm going to cut off being underground at 4 minus x, whatever x is. Now I'm going the rest of the way underwater. How can I figure out how long the hypotenuse is?
Use Pythagorean theorem.
Pythagorean theorem. So this is x and this is 1. So this side's going to be the square root of x squared plus 1 squared?
Yeah.
Yeah? So square root of x squared, and you guys all agree 1 squared is 1? Okay, so I want you to explain to each other why the distance from, and I'm actually going to add some points here. Let's call where we start the power station P, and then we'll call this Q, and then we'll call getting to the island I. So explain to your partner why QI is the square root of x squared plus 1. Okay? Explain to your partner why the distance from Q to I is the square root of x squared plus 1. And at home you can explain it to yourself, hopefully. Pythagorean theorem.
Uh-oh.
Okay, all right, so we've kind of worked out a lot of stuff about our diagram here. So I'm going to say the cost underground we know is $30,000 for each mile that we lay underground. And we decided that that was going to be represented by 4 minus x, the distance from P to Q. And then it costs more underwater, so $50,000 times the square root of x squared plus 1. That's the distance we've decided we're going underwater. And then I can write it as c of x. I want to make it easily differentiable, so I'm going to distribute there. So I got 120,000 minus 30,000 x plus 50,000 times x squared plus 1 to the half. Now, if you remember back to yesterday, I said that most of the time you're going to use the second derivative test to discern whether you have a maximum or minimum, but sometimes you'll be given a closed interval. And then you can just test the endpoints and the critical point. Okay? This is one of those cases where it doesn't directly give you the interval, but it's easy to think through what the interval is. Because if you look at this, when we derive it, it's not going to be, we're not to use the quotient rule to get the second derivative. Okay, which, it's annoying if we don't have to. We could, for sure. And if you love using the quotient rule, like I really like it, then that's a way to go. But I can easily imagine my closed interval here. Because if x were 0, x was 0. This distance from here to here was 0. That would mean I would go 4 miles underground. You guys agree with that? And 1 mile out to the island. Okay? So that's a possibility. X could be 0. And then I would go the 4 miles underground and the 1 mile out to the island. Okay? If x was 4, so it took up this whole thing, that would mean I'm going straight from the power plant to the island. I'll just draw like a line on here. I'd be going all the way underwater. Does that make sense? I just wouldn't go under land at all. I'm going to go all the way underwater if x were 4. It took up this whole spot. Okay? So those are my flow. That is my closed interval. Okay? And all the cable problems work that way. So as long as you can figure out what happens when x is 0, and I always make it this little distance in here. That means you're going all the way and then perpendicular. And when it takes up the whole way, you're going all the way on a diagonal. Okay? Thumbs for that? Yeah? We've got the interval. So now that we have an interval problem, the way you solve one of those max or mins is you find c prime at x, find your critical number, test it in the original, test your endpoints in the original, and see which one gives you the minimum cost. Okay? All right, so that's our plan. So we're going to find c prime at x. So derivative of 120,000 is 0. Derivative of this is just negative 30,000. And then I need chain rule for this. So the half is going to come down and multiply the 50,000. Give me 25,000. Times x squared plus 1 to the negative 1/2. And then then times 2x. Very good. Chain rule. So I need the derivative of what's inside, and that's the 2x. Okay? Now I want to set c prime at x equal to 0. Of course there's a chain. Plus, okay, so does everyone see that I can multiply the 25,000 and the 2x together? They're all being multiplied, and that's going to give me 50,000x. And then I'm going to bring that down to the bottom and make it the square root of x squared plus 1. Okay? That's where I was saying if we were getting into the second derivative, I would need the quotient rule here with the 50,000x over the square root of x squared plus 1. Okay? Owen, what are you doing? Okay. All right, so I'm going to Sorry?
You would report it to the design.
I'm gonna add the 30,000 to the other side. And it's not hard to solve, it's just you haven't seen one, sorry, I forgot the X there, like this, in a while maybe. Anyone have any ideas? Yeah. Oh, not yet. I am going to square both sides, but not yet. First thing I'm going to do is multiply both sides by the square root of x squared plus 1. So I've got everything in the top. So these divided out. So now I don't have a division anymore. I also, if I don't want to deal with 30,000 and 50,000, I could divide both sides by 10,000. I'm okay with that. And then I'm dealing with smaller numbers here. So that's going to leave me with, before I square both sides, like Anna suggested, I want my numbers to be more manageable. And now we're going to square both sides. So we're going to square this whole side and this whole side. Be careful. So what happens when you square the left side? Very good, 9 times x squared plus 1. So this squared undoes that square root. Everybody good? And I also have to square the 3. And then on this side, 25x squared. Yeah? Now I can distribute the 9. Yes, squared. The numbers work out so nice in this problem too. I just love it. Then what about next to Yasha? Not yet. Divide by 6. So I've got it down to x squared is 9 over 16. And now I square root both sides. And I get positive or negative, square root of 9 is 3, square root of 16 is 4. As my critical numbers. But which one can I ignore because the negative. So I'm going to ignore x equals negative 3/4 because it's not in our interval 0 to 4. Okay? 3/4 is in our interval 0 to 4. So we're going to sub 0.75 in for our cost, and then we're going to sub 0 and 4 into our cost and see which one ends up being the smallest, because we want the least expensive one. Okay? So now we're going to test C at 0.75. So C, right? Like that's at the very beginning. I think I'm running out of room. I think I'm going to have to do it over here. I won't have room. Okay, so can someone read out what our cost equation was?
30,000 times 4 minus x plus 50,000 times the square root of x squared.
Thank you very much, Lynn. And then we're going to test C at 0.75.
Are we keeping it in a fraction or are we keeping it decimal?
It's up to you. It's nicer to have the 3/4 in here, but we can get our answer this way. So just have to be careful when we're typing the pieces into our calculator. That should be at 30,000, my bad. There's 0 here. So this part I got 97,500 plus I got 62,500. So in total, I got $160,000 if I use the critical value. Okay? Now I've got to test the endpoints. So I want to find C at 0, sorry. So if I sub 0 in here, I have 30,000 times 4 plus 50,000 times the square root of 1, which is going to give me 170,000? So far this is a minimum, but we also want to test C at 4, which would be going all the way underwater, which probably is not going to be cost effective, but we'll figure out whether it is or not. 30,000 times 4 minus 4 plus 50,000 times the square root of 4 squared plus 1. So that's going to be 0. Square root of 17 times 50,000 is $206,000, 155.28. So if we're comparing our 3 costs, this one is the minimum cost. And then we want to make sure that we answer the question that was actually asked way up at the top of the page. So the question asked, what is the least expensive way to lay the cable? So it's going to want to know how much do you put underground and how much do you put underwater. Asha?
Would it be the,
So we know that this here, Asha, is 0.75 miles. Does everyone agree with that?
would be 3.25 miles underground?
Good. So 4 minus 0.75 is going to give me 3.25 miles. That's going to be the underground part. Does that make sense to everybody? And then here, I have to sub in the 0.75. So I'm going to be, Q to I is going to end up being the square root of 0.75 squared plus 1. Yeah? Okay, so I want to get that distance. So the square root of 0.75 squared plus 1 is 1.25 miles. So in my statement, I'm going to say that I need to go, the least expensive way to lay the cable is 3.25 miles underground and 1.25 miles underwater. Yeah? Yes. So the other way of doing it without the closed interval is to find the second derivative from here, which you're going to need the quotient rule to do, and then sub in and make sure that you get we're looking for a minimum positive number when you sub the critical point.
That's the other way. And the other option is to look at the endpoints.
Yeah, yeah. Those are the 2 options, right?
Is this the easiest and shortest way, or is it quotient rule?
I feel like this is the easiest way, but it's totally up to you. Okay, if you just like, okay, I'm always getting second derivative and I know what if it's positive, it's a minimum, if it's negative, it's a maximum, then you might need some extra paper, but maybe I like doing the quotient rule, and I think I did the quotient rule in the solutions. So you can see both ways and see kind of which one makes you feel better.
Should we practice using rules or just pick one?
Pick one and pick the one you like. Like cable problems are all the same stuff. Okay? Numbers just change. All right, so we still haven't said our final statement here. I think it was, well, let's refer to the picture. So we want, whoops. We want, therefore, lay 3.25 miles of cable underground and 1.25 miles of cable underwater to minimize the cost. Yay! Okay, so now we've gone through between yesterday and today, 6 of the most famous types of optimization questions you're gonna get. Okay? And you're just gonna spend time practicing them now. So this is stop, right?